In this lecture, we shall be looking at free fall. In free fall, let's consider the motion of an object along the vertical axis. In this case, we are talking about the y vertical axis. Since the object is in free fall, we're going to start off by assuming that there is no air resistance. So that's why we call it free fall motion. So the object falls under the influence of gravity alone. So it has an acceleration, which we shall call the acceleration of gravity. We will be able to use our kinematic equations for free fall motion also. So we'll start off, our acceleration is the acceleration of gravity. Let's look at the next frame. So in this frame, we looked at equations for, we've looked already at the equations for uniformly accelerated motion. Free fall motion is a lot like uniformly accelerated motion since the acceleration is constant along the axis. So if we take our motion, a one-dimensional motion along the x-axis, we had kinematic equations given by x final equals x initial plus v initial delta t plus half a, and in this case, this will be a subscript x. Let me just write x, a subscript x delta t. Actually, let me just make this look nice. So I'll use a medium point. So this is x. So this is a subscript x. So this is our motion along the x-axis, and then for final velocity, again, we shall have the same, we shall have kinematic equations where we're using the a subscript x as our uniformly accelerated motion along the x-axis. So v final along the x-axis is given by v initial plus a subscript x delta t. So these were our kinematic equations in one dimension for motion along the x-axis. We can just rewrite the same kinematic equations for free fall by replacing the x with letter y and replacing the acceleration in the x direction with acceleration of gravity a sub a g with acceleration of gravity g. So we'll continue with that in mind. So this is again one of our kinematic equations, and so in this frame I'm just repeating what I've already said, which is that we shall be replacing acceleration a by letter g, where remember acceleration of gravity g is negative 9.81 meters per second. The negative sign is a convention that we've been using, which is that acceleration is a vector, so any vector pointing down is negative. So we're using a convention that motion downward is negative. Let's look in this frame at our kinematic equations for free fall motion. So we are going to replace a with g and then just write final y position is equal to initial y position plus v initial delta t plus half g delta t squared, where this position would have been a, but we replaced the a with g. And again, find the kinematic equation for final velocity is equal to initial velocity plus g delta t. And in this frame here, v final squared is v initial squared plus 2g delta y, where delta y is the displacement along the y-axis, which is you can think of that as the height. So I just remind you here that we've replaced the variable x by y since we are working along the y or vertical direction. So in this frame, we can look at the graphs for free fall. So let's start off with a position time graph for free fall motion. So in this position time graph, this is the y-axis, and that's the time in seconds. And so the object starts off at some initial position high above the ground, and then its position changes slowly initially. When you drop it, then the position becomes larger and larger as it falls, and so that's why we have the curve looking the way it does. And in this frame here, we can look at the velocity time graph for an object in free fall. So I've drawn the velocity along the vertical axis and time along the horizontal axis. And so the object falls initially. So suppose we just drop the object, its initial velocity will be 0, and it will just increase and become more negative as it goes downward. Because we are going down, the velocity is negative, or it's on the negative side. And so it just increases uniformly as the object goes down. In this frame, we can look at acceleration time graph for the object. Again, we draw acceleration on the vertical axis and time on the horizontal axis. And so, since the object is uniformly accelerated with an acceleration A equal to the acceleration of gravity, since it's going downwards, our vector convention tells us that acceleration will be on the negative side. So we just draw a straight line on the negative side of the axis. So this is negative 9.8 meters per second squared. I just write that there as meters per second squared. Meters per second squared. Okay, let's continue. So we go next to this frame. So in this frame, I'm giving you an example. So a rock is dropped from a 50-meter tall platform. Find 1, the distance that the rock falls in 1 second, and 2, the speed of the rock after falling for 1 second, and 3, the position of the rock after 1 second. So we can do that in the next frame. So I'm giving you about 5 minutes to do it. So take about 5 minutes to do this exercise, and then we can look at the solutions in the next frame. So here are the solutions that I've received from you students. So after falling for 1 second, the displacement along the y-axis is 4.9 meters. And we can find that by using our kinematic equation, delta y equals v initial delta t plus half g delta t squared. Since the object is dropped, initial velocity is 0, the time interval is 1 second, acceleration is negative 9.8. So you plug this in here, and you have 0 minus half times 9.8 times 1 squared, which gives us negative 4.9 meters. So don't forget that since it's the vector quantity, displacement is a vector quantity, negative just tells us it's going downwards. Okay. In the next frame, let's look at the final velocity. So somebody told me the final velocity was negative 9.8 meters per second. So we can look next at that. So we use our formula V final equals V initial plus G delta t. Our final velocity then is equal to 0 minus 9.8 times 1, which is negative 9.8 meters per second. So that is correct. We'll put a check mark by that. Let's go next to delta y, the displacement. So we can look at the final position after it has fallen for 1 second. So it starts off with an initial position at 50 meters. It falls after 1 second, it has fallen 4.9 meters. So this is the position y final. Okay, so y final is equal to negative 4.9 plus 50. So initial position is 50. Okay, so y final minus y initial equals 4.9. So we're looking for y final. So the final position after falling for 4.9 meters is 45.1 meters. So it's still high up there. It's at the 45 meter mark. Okay. Then let's look next at how long it takes for the rock to hit the ground. So we'll do that in the next frame. So this implies looking for a time interval delta t, which is the time it takes to fall from a height of 50 meters to a ground, which will be at 0. So we use our kinematic equation delta y, which is equal to v initial delta t plus half gt g delta t squared. Note that this delta t here is an answer that you guys gave me in class. So I'm just going to check that by using our kinematic equations. So we know initial velocity is 0, so this portion goes away. So let's go down to the next frame. So in this frame, we can say delta y is equal to half g delta t squared. And so we just solve for delta t. So we rearrange as shown here. Delta t squared is given by 2 times delta y divided by delta g. So it's 2 delta y over g, not delta g. So delta t is the square root of 2 delta y over g. And so we just plug it in there, 2 times negative 50 over negative 9.8. Remember, the displacement is starting at initial position of 50 and going to 0. So the displacement is minus 50. And since acceleration is negative 9.8, we put the negatives in and you see they both cancel out. So we have 3.194. We take the square root. So we want to be sure that you understand that we cannot have a negative square root, so that's why I'm putting the negative in to show you how they cancel out. So let's look at the next frame. So we use delta y equals negative 50 meters because of this fact that delta y is final, y final equals y initial. The initial position is 50, the final position is 0. That's how I ended up with that. So I put the delta over there. Okay. So that is the end of our lecture on free fall.